Hello again. It seems like we are forever learning from videos. I feel kind of bad that this unit haven't really done a whole lot of face-to-face teaching to you guys. Alright, again, this warm-up you do not need to have in your warm-up book. I won't have a whole lot of warm-ups to check at the end of this unit, huh? And we are at the end of the traditional or more straightforward integration techniques. So remember, the quiz that we're going to take on Friday is going to be on integration 1 all the way through 5. So this is the last one that's going to be on Friday's quiz. So wanting to make sure you recognize when I ask you for the general antiderivative, or I could just say the find the integral versus evaluate. If I asked you to evaluate an antiderivative or evaluate an integral, I would have to give you limits of integration. Now, I gave you this problem on purpose because yesterday you learned one of the things you added to your list was that the antiderivative of 1 over x dx, which is of course asking for the antiderivative of x to the negative 1, for which power up when you won't work, is ln of absolute value of x plus c. But I need you to know that this is different, right? This is not the same thing. Think of this as the antiderivative of ln x times 1 over x dx, right? This is the integral of a product or the integral of a quotient in this form. Either way, I can't antidifferentiate that. Right? I can't deal with a product or a quotient unless it matches one of my formulas directly, or I can do an algebra rewrite. Neither one of these match my formula, match my formula sheet, and there's nothing I can do algebraically. So the only thing I can do is use substitution, but when I look at these things, I think of x being inside ln. That's not a use substitution, and certainly even if it was, the derivative of x is just 1. What am I going to do with this 1 over x? Then of course I make this x to the negative 1 as u. X to the negative 1, its derivative is not ln x, right? Its antiderivative is. So I begin to lose hope. So here's something that wouldn't occur to you probably until someone shows it to you, but now I'm going to show it to you. What if I make ln x to the first power? I make not x, but all of ln x inside the first power, and I call that u. Then the derivative of u with respect to x is 1 over x dx. Well, looky there. My u, excuse me, is right there. It's inside stuff to the first, which I know how to integrate stuff to the first. And du is directly right there. I have covered everything up except my integral sign and my to the first power. So I can directly substitute and rewrite this as the antiderivative of u to the first du. And anti-differentiating u to the first gives me u squared over 2 plus c. Since it's not a general antiderivative, I have to put u back in terms of x. Be very careful that you don't mix up your log rules, right? ln of x squared, you cannot use the log bring it down property, right? ln of x squared is not the same thing as ln x squared. ln x squared can be written as 2 ln x. ln x squared is just ln x times ln x. Those two things are not equal. Now, you might be wondering why I'm asking you to find a derivative of inverse trig. Because guess what? One of the things we're going to do today is do the antiderivatives of inverse trig. So just remembering what the derivative is. The derivative of inverse sine, remember, gets rid of inverse sine. It's 1 over the square root of 1 minus the stuff squared times the derivative of the stuff. And my stuff is 5x squared so this simplifies to that's the derivative. Now, would you recognize, right, the question today is going to become, if I ask you to anti-differentiate that, would you recognize that came from inverse squared, that 10x got spit out of the 5x squared that's in here that got squared? Worry. Alright, before we do that, I do want to remind you of this integrand up here. So far you do know how to integrate 1 over x dx. And you know how to anti-differentiate ln x as long as the derivative of ln x is here, is 1 over x, right? Ln x to the first times 1 over x. You know how to do that. You do not know how to do anti-differentiate ln x. That will be after integration 1 through 5 is where we'll learn how to do that, but there is no direct rule for that. That is something we need another anti-differentiation technique. So, speaking of logs, remember that we did integrate ln x as long as that 1 over x was there, right? We can't just integrate ln x dx, but we could as long as its derivative 1 over x was there. So, what about integrating log base 2 of x, right? This base 2 becomes a little problematic. As long as I have, again, the derivative under here, right? The derivative is here. I'm going to rewrite log base 2 so that it looks like this, right? Here's where I'm trying to go. I already know from the warm-up how to anti-differentiate this. I've got the x and the dx. I do have logs, I just need to get that into ln, right? So, fortunately, you took Algebra 2 and you paid attention, and so you remember how to rewrite into a base, right? You remember the change of, I called it the ace of base property, but the change of base property. To change your base to any base you want, log base b of x can be rewritten as a quotient of 2 logs, where the old argument is still the argument of the numerator, the old base is the argument of the denominator, and then you can insert a for any base you want as long as it's the same base, numerator and denominator. So ignore the x dx part right now. We're just going to take log base 2 of x and rewrite it. So I'm going to keep this 1 over x dx over here, and I'm going to take log base 2 of x and do the change of base property on it. So I'm going to write log old argument over log old base, and then I'm going to insert any base I want. I'm going to do any base I want. Given the warm-up, I'm going to go to base what? And of course we don't write loge, we write ln x, and I'm going to do this, times 1 over ln 2 times 1 over x dx. There are three products there. One of them is a constant. Can you see it? Since I don't know what 1 over ln 2 is, but it's a constant, what can you do with it? Osmosis. So, look at what I have now. I have 1 over ln 2, and then I have the warm-up. Remember with the warm-up, we made ln x to the first. We called that u. This is du. So we have 1 over ln 2 times ln x squared over 2. Of course, this 2 can come in front, so this could actually be 1 over 2 ln 2, which remember they might write as ln 4. And then put this ln x squared on the top. Remember, if it's long answer, it doesn't matter how you leave the final answer, right? But for multiple choice, which is what these kind of problems will be, it's going to look like this. Most probably. Now let's do a problem like that, but with the same problem, only let me put limits of integration on it. So the exact same problem, but it's a definite integral because I have x numbers. So I'm just going to go straight to the answer. Remember we a sub base that. So I had 1 and 2. 1 over ln 2, and then we had ln of x, we raised it to the first, times 1 over x dx. This was our u, and this was our du. And again, I'm going to take, if u is ln of x, I'm going to say what was u of 2, which is ln 2, and u of 1, which is ln of 1, which is 0. So 1 over ln 2 times ln of 2 squared over 2 minus 0 squared over 2, which of course is 1 over ln 2. Remember, you cannot bring that 2 down, but you look what I'm going to do. I'm going to write it like this, because bam, baby, and I just end up with 1/2 ln 2, which of course AP might write as ln times the square root of 2. Oh snap. You see why for BC Calculus, doing these kind of problems over and over again, your algebra's got to be fast and strong, right? So, integrating log base e or log base 2 is not doable unless the derivative 1 over x is there. But if the derivative 1 over x is there, check. In the integrand, I can take log of any base and rewrite it into ln. So let's try this one. Okay. So, only because the derivative of ln, 1 over x dx, is here, can you say, oh, let's make this a u. Only I'm not going to make it u first. first, I'm going to say, I'm going to put the 1 over x dx way over here. And here's this to the cubed. And then inside, I'm going to a sub base. So log base 4 is a ratio of 2 logs. I'm going to change to base e. Old argument, old base. The denominator, ln4, is a constant. Let's osmosis it out, but it's not just ln4, is it? It's ln4 what? Cubed. And now I have the warm-up problem again. Ln of x cubed left inside the integral, but its derivative 1 over dx there as well. This is a very specific case. It's just AP likes it. So now this is my u, and this is my du. This is a general antiderivative, so I don't have to worry about any limits of integration. How do I integrate? This is u. I'm integrating stuff cubed, and this is du. So how do you integrate stuff cubed? Right, or u cubed, it's u to the 4th over 4 plus c. And what is my u? See how I'm skipping a couple steps here? Okay. Oh, space. Woo! Alright, now we're going to do some inverse trig formulas. So these you just need to get out your sheet and write them down. They're a bit of a dagger because they're annoying to look at and annoying to remember. Again, for AP, this is down on your list. In May, these are not heavily tested, these formulas. We're going to test them on your quiz and on your test. But then in May, you don't worry about them that much. So I'm going to give you 3, and you should recognize them. What is the derivative of inverse sine? 1 over the square root of 1 minus x squared. What is the derivative of inverse tangent? 1 over no radical and a plus sign. What is the derivative of inverse secant? Most annoying because it's got this absolute value of x thing here. Do you remember that? Now you might want to ask yourself, how come I only gave you 3 formulas? Hint. Starts with C, starts with C, starts with C, right? They're all the same formulas, just negatized. Now here's the interesting thing though. If you actually osmosis the negative outside, right? This integral, if you osmosis the negative outside and turn this positive, this is what? Inverse sine. So, right? You really, what's the nice thing about inverse trig is that really you only have to remember 3 formulas because you can always just osmosis the negative out of there. Right? Cool beans. So yes, do pause this, write this down on your sheet, right? You should have in your notes, I know you have them all throughout your notes, but you should organize and have an antiderivative formula sheet. Right? And number 1 should be the integral of x to the n. Right? And number 2 should be regular trig. Now you can complete the regular trig, right? You can put it all in one place, you know? Blah, blah, you know, and blah, 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 blah. And I've given you a bunch of formulas you should have on there. Let's do some more, let's do some examples using inverse trig. Start nice. Okay. What does this look like? It's got a radical and it's got the squared minus, so I'm thinking inverse who? Thinking inverse secant. So I say to myself, this inverse secant? But aren't I supposed to have the absolute value of x? What's going on? Look at my limits of integration. Do I need the absolute value sign? Right, so that's a little bit mean. But since both values that you're going to be plugging in are positive in for x, the absolute value signs aren't necessary. Now, I do want to tell you that oftentimes, especially in May, you're going to look at this problem and you're going to think use substitution first. Right? You're going to say, oh, if I make this u, because this is stuff to the 1/2, and then the derivative of u is 2x. Oh, look, there's an x down there. But remember, that's not an, you know, even if you move the 1/2 over here, this x is x to the first. What is this x? That's actually x to the -1. U substitution isn't going to work. That's the hardest thing, I think, for kids to deal with antiderivatives. You might very well start an antiderivative and think it's U substitution, and then it doesn't work out. And if it doesn't work, it doesn't work. If the derivative of the integrand isn't inside, the derivative of u isn't part of your integrand, you're stuck. And when you're stuck, the things that you do are think rewrite, or is there a trig rewrite, a log rewrite, an algebra rewrite that gets me out of this, or is it a formula that I don't recognize? And so to me, inverse secant in May, when I'm sitting and taking this, doing this problem in May, I wouldn't have thought inverse secant first. I would have thought use substitution and then go, oh wait, that doesn't work. Then I would have gotten myself to inverse secant. So sure enough, this is inverse secant of x, evaluated, and no use substitution necessary, which means I'm going to have inverse secant at A and B, and this now just becomes a trig exercise, right? I don't have my inverse secant values memorized, but I can say to myself, this is a reciprocal. Who has a cosine of 1 over root 2? Who has a cosine of root 3 over 2? And remember, we are only dealing with, right, function values. I don't have a limited, I don't have a whole bunch. Who has a cosine of 1 over root 2? Pi over 4, right? Who has a cosine of root 3 over 2? Cosine of root 3 over 2? Pi over 6, right? So of course get a common denominator. So that is right? Don't know why that disappeared. Forgot to get it back. Here, second up. Alright, who does this look like? So I have a radical. Again, the first thing I would think about, if I'm looking at this, especially in May, I think to myself, oh, this is going to be a u, right? There's my u. So I say to myself, u is 1 minus x to the 6th. du is negative 6x to the 5th. And I've only got an x squared. Cry. Use substitution doesn't work. Okay, there must be an algebra rewrite, or what the heck? Why can't I erase this stuff? Must be an algebra rewrite or a formula I don't recognize, right? So I think about some algebra and then I'm like, oh, wait a second, there's a radical in the denominator with a 1 minus. And I say to myself, I do have to think a little bit of an algebra rewrite. Inverse sine is the square root of 1 minus something squared. Well, how can you rewrite x to the 6th? That's right, x cubed, and things should start to fall together now, right? Oops, I forgot my dx, didn't I? Ugh, terrible at that. So, if I make my u what's inside the square there, x cubed, du is 3x squared. I've got an x squared, I just need to get rid of that 3. And now I've got substitution. There's my x cubed, that's u. The derivative of x cubed is x squared dx. I move the 1/3 over. And now this time I'm going to be copying over, because what I'm going to be anti-differentiating is, right, 1 over the square root of 1 minus stuff squared. And of course that is what? Inverse sine. Oops, gosh darn it. So this is the integral of 1 over the square root of 1 minus u squared, and then x squared dx is replaced with 1/3 du. And now anti-differentiate. And put the u stuff back. Yeah, Dylan. About a half hour. Bye. Excuse me. I don't know why these all aren't going away. Anywho, alright, so this one is a little bit of a dagger. See the dagger there? Now I'm going to go ahead and copy this over on the white screen, because for some reason my eraser stuff isn't working. P.S. Did you just notice that my son called me from upstairs? So lame. You kids today. So let's see why this is why this one's a dagger. Gosh, my integral signs are ugly on here, aren't they? So I gave you the slurping sound because this is another one of these where you've got to recognize, right? And I don't recognize it right away. Don't beat yourself up if you don't recognize this stuff immediately. I go through a thought process. It's just that I'm faster just because I've got more experience, that's all, right? You think about u substitution, again, you're like, oh, that's 8x, and no, there's an x, but remember that's not an x, that's an x to the negative 1. As soon as I see a variable outside of this radical, I'm thinking, oh, is that a, is that a inverse secant thing? And yes, they should have absolute value. They don't have absolute value simply because it's going to get in my way. But if I think of this as, let's see if I can write a prettier integral. Because inverse secant has a radical, it has a -1, but it has x squared, doesn't it? So what could I put in there to create my u? Right? So u, so this is actually pretty tricky, right? If u is 2x, du is 2 dx. Now don't get confused with this x. This x is red. It's still part of the inverse secant, right? So if u is equal to 2x, this substitution is going to be a little bizarre, right? I'm totally fine with this. There's my u. I'm okay with the fact that I can get rid of this 2, move it over so that I have a dx. Right? This just becomes 1/2 du is equal to dx. So now when I go to do a direct substitution, though, something weird happens. I have an integral. I'm okay making the dx. The dx part I'm going to put first is 1/2 du, right? That's just, right? That's just the dx. For the dx, I put 1/2 du. Now I'm just going to put a 1 right there. Now I'm going to put a 1 over, I'm going to circle that so I don't forget it, and I'm going to put the square root of u squared minus 1. But I can't just, right? So check the dx, check the 2x, but I still have this x floating out here. What the heck? What do I do with that? How do that's got, right, this is a u, I have a u and a u. Gosh darn this x, it needs to be a u. Gee, I wonder how I could rewrite x in terms of u for this problem. If u is equal to 2x, mustn't it be true that u over 2 is equal to x? And if this is u over 2 here, right, I'm just going to put u over 2 here. Let me suck this 1/2 out. This 1/2 I'm going to put out here, right, osmosis, 1/2. Now I have 1 over u over 2 times 1 over the square root of u squared minus 1. But isn't this just somewhere I lost my du, didn't I? Just gonna stick it at the other side. And then shocker, osmosis this 2 out here, and I just end up with 1 over u times the square root of u squared minus 1 du, and oh my god, that took forever, but I got to inverse secant of u plus c. Of course my u, way back from the beginning, not x, what is my u? My u is 2x. Oh, this is Ms. McDonald telling me she thinks that tomorrow we will have a delayed opening. Oh, yay. So the clue to this one again was not being frightened by the no absolute value, just deal, and then realizing that this 4x squared needed to be 2x squared. And then this tricky x out in front. still all goes back to u substitution. This one is a multi-dagger. So, again, first thing that you're probably going to think is u substitution. Oh, u is 9 minus x squared, du is negative 2x. I don't have another x floating around here. There's no algebra I can do with that, and it looks so. I'm thinking with a radical in the denominator. This is maybe inverse sine. And the only reason I'm thinking that is because it's got a minus x squared here, right? A constant minus x squared. But to deal with inverse sine, don't I have to have what minus x squared? It needs to be a what? It needs to be a 1. Alright, come on algebra. This is when is your algebra good? Or is it not? This is one of the times where it really shows up. And again, you're not going to maybe think of this off the top of your head, but once I show it to you, hopefully you can see the type of algebraic rewrites and manipulations that higher level math and science are really going to require of you. So, watch this handy dandy trick. I really, really want that 9 to be a 1. How do I make that happen? See what you want, make it happen. Unless, of course, you're at a store. Isn't it true that 9 over 9 is 1? That's true, but that's not legal, is it? If I'm going to divide the 9 by 1, what do I have to do to the x squared? By 9, excuse me. So I got myself a 1. Remember, this is where I'm trying to go. I think this is where I'm trying to go. So I'm desperately trying to get there. So now 9 divided by 9 is 1. But that's not legal. I can't just randomly change that, right? But I can multiply by 9, right? Isn't this now the same thing? Right? This is, do you believe that 9 times 9 over 9 minus, distribute the 9 here, is still the same as this? Right? It wasn't before. If you cover up this 9, you can't just randomly divide both things by 9. But now I have 9 times 1 minus, and now remember, I was trying to freaking get to x squared, not x squared over 9. But check out this magic. What is x squared over 9? Look like if you pull the square to the outside. Oh, hey, I need that 9 to be out of there. Well, that's the square root of a product. So isn't it true that this 9 can come out of the radical and be a 3 right there? Now look at this coinky-dink. U is going to be the stuff inside the squared. So what is du going to be? Check out that magic. Here's u, and here is du. And all the rest of that red stuff is inverse sine. Do you see it? The 1, because of course there's a 1 anywhere I want. And then I have the radical, and I have the 1 minus stuff squared. So there's no osmosis with that 1/3. It's part of the du, right? So now, write it like this. Write the I replace the x minus 3 with the u. I replace the 1/3 dx with a 1 du, and then this is just inverse sine of u plus c, but my u was x over 3. Now what if with all that crap you're like, whatever, Ms. Guz, whatever? How can you check your work? What is the derivative of my answer? The derivative of inverse sine is 1 over the square root of 1 minus the stuff squared times the derivative of the stuff. And what does that look like? 1 over the square root of 1 minus x squared over 9 with the 3. But of course you could rewrite that as 1 over the square root of 9 times 1 minus x squared over 9. And shocker, what is that if you distribute the 9? Ta-da! Alright. So that's the last of the examples. Print out integration number 5. If we have a delay tomorrow, my period 4 that already took the test will, we will just do this lesson tomorrow, and as much as we get through, and then you can watch the video for the rest. And my period 6, you will take the test, the last part of the test finally, and then watch this video in, after school. And on Wednesday we will have just a big practice day. Okay? Alrighty. Well, this has been fun. It's been real. But I do miss teaching you face to face.